All right, well, thank you everybody for attending today. My name is Nicholas and I'm part of the Applied Stats and Programming Committee on ATSA. So just for encouraging people to join the committee next year, we organize these kind of workshops. Art enthusiasts and like programming language enthusiasts. So yeah, just reach out and don't hesitate. I'm very pleased to introduce Dr. Adrian Correndo today. He did his PS and Masters in Argentina under the guidance of Dr. Fernando Garcia. And back in October 2021, he obtained his PhD degree here in K-State, Chiappini. He works mostly, he's specialized on applied soil fertility and applied statistics. So today he's going to share some of interesting stuff he has been working on tidy mixed models in R. So yeah, thank you, Adrian.
Good. Thank you very much, Nico, for the introduction and everybody to join us today. As I was part of this committee of applied stats and programming, so I'm very glad to support the activities. I mean, as long as I can, I will try to do my best supporting the team. As always like to say, this is not a teaching session. I'm not teaching anything. I'm just sharing what I've been working with, and we are kind of learning together, right? So I'm just sharing the coding that I've been able to put during the last couple of years in some of the works that I've been involved. So today we are trying to cover a topic that it wasn't covered by last session of the applied stats, the mixed models, which is a very hot topic in agriculture. They are very common, but how we analyze this type of data sets is always confusing and it's stressful for a student. So here I'm just bringing two examples. One example is with the SplitPlot design, which is very common, mainly due to practical reasons. We are going to talk about more later, and also repeated measures. With the SplitPlot, we are kind of going to warm up with that example. It's just a fake data set. So the idea is just to get the core concept behind the SplitPlot and how we should analyze these cases. And later on, we are going to cover a repeated measures analysis, and that will be basically reproducing the analysis that I've made from one of my papers. So basically, we're trying to reproduce one of the figures that I made for that paper. So if you are able to read along the article, you will find all the details. So all you need is there on the web page that I share. So if you just go here on the, let me see, if you go here to the GitHub icon, and then you open that, you will open the repository where all the files and stuff is. Okay, so here you have all the code that you need. And if you don't have it this way and you want to download to your computer, you simply need to download this as a zip file. And then you open this wherever you want in your computer. And you will be able to, since it's within a project, you will be able to run it as it is. As I recommended in the email, we are trying to work with this new type of files, the QMD, that they are the cuarto. This is the new development from the RStudio guys. This is basically the new version of the R Markdown, which is the type of files that we may use to create reports, websites, blogs, many type of products behind the data analysis. Okay, so the idea is that if you have the latest version of RStudio and R, you will be able to reproduce fully all the code that I share. Otherwise, what you can try is, if you see here this menu code, if you click on it, you will have this option that is view source, and there you have all the code. So here you can just select all, right, and copy, and then you just paste in a file that you have on your machine. Okay. Okay. So first of all, let's start with what mixed models are, okay? Mixed models is basically, as the word says, mixed because we are mixing fixed effects and random effects. The way I understand this is simply that we are having effects or factors that they have an impact on the expected values. Those are the fixed effects, but also you may have some factors that they are not affecting the expected value, but they are affecting the variance. They are affecting the uncertainty we have when we are producing an expected value. Okay, so that's basically it. We have in the same model these two types of factors: fixed factors affecting the expected value or mu in the model, and then you have random factors which basically will affect the sigma components. Okay, so that's the main definition. Today there are many different types of mixed models. Today what we are going to cover is a special case, the linear mixed models, LMM, as you may find across the internet and literature. And basically they follow a certain set of assumptions, right? First of all, if we are talking about linear models, we expect that the model is basically a linear combination of these different factors, okay? Then we also need that the distribution of the response variable is normal, okay? It's Gaussian. We may have another options, but with linear mixed models, we need to fill this assumption of normality. Gaussian is basically a normal distribution, right? It's a more formal name. And then we also assume by convention in this type of models that the random effects are normally distributed with an expected value equal to 0, right? So that's why they don't have an effect on the expected value, a mu, right? Because they will compensate, right? All the random effects that you may have, they will compensate and they won't affect the prediction, but they will affect the uncertainty on the prediction. They affect the sigma, okay? So that's why here I put they have an effect equal to 0 on mu, but they have a positive effect on the error component, okay? So they are basically additive to the variance. Today, we are going to cover examples with two of the most famous packages in R that they are useful to cover this type of models. One is NLME, which is stand for nonlinear mixed effect models. Nowadays, this is part of base R. It's a very important package for statistical analysis. And I would say that is the most compelling one because it allows us, as you may read here, to specify different structures of the error, even if we are not fulfilling this assumption of homogeneous variance. We may still work with models that they don't have homogeneous variance. We can model the variance, and the NLME have options to work with that. That's something that the LME4 doesn't have. The LME4, you can add random components, that's okay. But if you have to specify certain structure of correlation or covariance, right, on your model, they are much more restricted as compared to NLME. Anyway, for certain examples, they both work well, okay? There is an important release that we got just yesterday, I think. This is the task view. I will click on it. So here you will find all the the main packages that they are in R covering different type of mixed models, from frequencies to Bayesian models, the more advanced ones, and generalized models, which are basically the ones that allows us to specify non-normal distribution, right? So just for the record, you have there available many other different resources to work with mixed models. And then why tidy, okay? Tidy, it's a philosophy behind all this tidyverse development that the guys from our studio have been putting in the last decade. Basically, I would say, from my perspective, tidyverse is probably half of R right now. So R is has become very useful for data scientists across many different disciplines because of these people that they were able to put a way of coding, right, that is much more friendly for non-statistician users, non-programmers. So thanks to these guys, we are able now to spend or to invest much of our energy trying to solve the problems that we have rather than to learn new, complicated one of programming, right? And in my personal opinion is that it's also one of the advantages when we compare versus Python, for example, which is a very powerful language. And for many other stuff like processing images is more powerful than R, but for statistical analysis and data science, R is much way straightforward. It's much straightforward than other languages. And most of this is thanks to this tidy data philosophy. So basically with the tidy data, what we are trying to work is with a structure of the data that it facilitates the implementation and the iteration of many different models across our data, okay? And comparisons and everything. So basically, the way that we arrange our data is in tables or data frames. The guys of Tidyverse, they call tables. That is it's not a table, it's not a data frame, but it's a table. So table is basically a refined way of data frame that it has certain properties that are more advantageous than working with lists or with data frames. So basically we'll have a table where each column represents a variable, right? Then each row represents an observation, right? And each value is in a cell, within a cell, okay? So that's the main structure. It sounds silly, but you can imagine how useful it is to define this structure to later start working and putting a lot of models and different things on it. And we can even store models within each cell. For example, we can store models inside. We can store plots inside. We can store many different things. So that's what I'm planning to show today. So today, for example, for the repeated measures models, we will have 4 locations that I'm not interested in comparing or sites I'm not interested in putting site as a factor. So what I'm doing is running 4 different analyses, right? For the 4 locations, but we run all at once, okay? So I will put a kind of, it's not a for loop, they call map function, but I will show you a way to run the same model to many different data sets at once. If you are more interested in exploring all the possibilities that we have these 2 books that they are free on the internet. You have the HTML versions that they are completely open. Otherwise, you can buy them in Amazon. Probably they are 30, 40 bucks or something, but they completely worth the investment. R for data science, I would say is more for traditional analysis, and tidy modeling with R is more focused probably on machine learning examples and more about forecast models. But they are all working with the same structure of tidy data. Okay. The outline of today, I try to represent this and I leave in you the code. Along the document, you will find these menus that they say show the code, right? So there you will find how to run all the different things that we have across the file, right? And this is all in the cuarto file. I will show you in a second. So basically, this is a way that we can produce a flow chart like this, very simple. And then I'm leaving a link there. So the idea is that once we have all these previous step of planning an experiment, conducting an experiment, collecting the data, cleaning the data, etc., we need to start exploring the data to see if we don't have any errors, right? Then after that, we will set as a group of candidate models. So we will perform this model selection step. After doing that, right, selecting the best model, right, they have the best performance, we may start doing the inference on our model, okay? So first we need to decide which model is best based in the check of if they are fulfilling the assumptions or if they have better performance indicators such as the AIC, as we're going to see. And then for the inference, we need first to test if there are significant effects. And once we test that, we may go and perform the comparisons. Okay, so that's a flowchart that we're going to follow today. So for the code, as I previously said on the email, ideally you will need the latest version of R and RStudio. So that way you will be able to create a cuarto file or to run directly the cuarto file that you have. As I mentioned, cuarto is a refined version of R Markdown that is a very useful source to open source software to create reports, right? So basically we can do all in the same file. We can create an analysis and a blog like I did here. This is all in the same file. So I running all the analysis, but also creating this blog to share with colleagues or with your advisors, etc. Okay. And there we go. So now for the packages that we need. First of all, there is one source that I like to use, that is this library, Easy Packages. If you don't have it, please install it. I just leave in a line of code above that. If you go now, we may go to the R. So this is how I see the same thing, but on my RStudio. Here I'm setting all the configuration, etc. So we're going to talk about later. And then you see here we have an outline. So for example, if I want to go to the package section, I go there, right? I just click and it's a kind of an index. And here we have this package that is Easy Packages. Within the code in this type of files, such as Markdown, is very similar, but the extension now is QMD. It's called Cuarto Markdown. Basically, all the coding, we can embed text, but in the middle of the text, we can embed what they call chunks of code. So they're basically small windows, right, with code inside. And then we have two different ways to see. We have this source, and also we have a visual option. So I'm going to go to source here. Oh, that help you? Probably we start. Yeah. Okay. Thank you. Okay. So I don't know, are all of you, were all of you able to open this file and see what I'm seeing now in the screen? Okay. Okay. So if we're here, basically we have this small play buttons on the top right within each of these small windows that they are basically, they are called chunks. For doing that, we can press Control, Alt, and M. Sorry, no, this is the commit. It's Control, Alt, and I, right? It's Control, Alt, plus I, and that we will open a new one, okay? And we have R here because we are working with R language. But the beauty of this is that you can work here with Python, for example, or with other languages. You just need to specify here on the top of the chunk which language you are using. Okay, so now we already created that. And here I'm just putting a title, right? So this chunk is about packages, okay? So as I was mentioning, we have these library packages, right? That basically what it's going to do is, if you have a package already installed in your machine, right? In your R, it will load it. And if you don't have it, it will install it and load it. So that is speeding up all the process of loading the packages, and it will recognize automatically if you don't have it. Here you have the comments. We are not going to in very specific detail to what every package it does. We are going to explore that along the code, but there you have the comments to let it explore. So basically we are from opening the files to processing the models, to obtaining means, to add letters to the comparisons. We are doing everything there. And of course, we are also producing plots, etc. And of course, we are loading these two libraries that I was mentioning before, NLME and LME4, that they are the main packages to run the analysis, to feed the models, okay? Two very special packages that we are using are the Broom and BroomMix, which are the ones I'm mentioning here. So basically, they will keep the structure that I was telling you, the tidy structure. They will put the models in the same format, right? So that way we can have our models stored within tables, within data frames. So that is very helpful. You see in a second. And there is a special extension that I have been developing very recently, that is BroomMix, that it allows to do this for this specific type of models, the mixed models. So there are three main functions that they provide that we are going to use today: glance, tidy, and open. You will see later on. So let's start with the SplitPlot design. Okay. So the SplitPlot arrangement, I call arrangement in purpose because it's not specifically talking about the design, because we may still have a randomized complete plot design, but with split plots in it. So the SplitPlot is basically an arrangement that we do because of logistic reasons. Sometimes it happens with irrigation, for example, right? Because we can move the pivot, right, to many different locations. So many times we have that constraining our randomization process, right? So what the SplitPlots are doing are constraining our randomization, okay? The main thing that we need to have in mind is that we have these two, we have a hierarchy structure, right? We have the main plots, which is the factor where we are going to randomize the subplots. So in the example that we have here in the data is, I will open here. In the example that we have here, if you already download, you can open with this code, right? That is a CSV file that is supposed to be, I will minimize this, sorry. I used to have the files here. If we are in our folder, right? We have different folders. We have the code. We are working here with this, but we also have a folder with the data, right? And within the data, we have these different options. We have 01 SplitPlot data as a CSV file. We also have the repeated measures data as a CSV of Excel file. But also, if you have a file on the internet, you may also do that. So I will show you in a second. So if you have a file in the code, you will find this. That is a URL address, which is basically going to my GitHub where the repository is, so you can open the file directly from there. So you should have this in the code I sent you, right? And it's in the web also. It's here, sorry. Here you will find this line. You just need to remove the hashtag from in the front. Okay. So now let's see, we just need to create an object, and we create an object like this. We may pass this minor sign and hyphen, and then we define the object, or we can directly use equal as well. So let me load, I didn't do that, sorry, but I will run the chunk entirely, and I'm loading all the packages I need. So that's the way to run all together. Yeah. You want white? May help? Okay. Okay. Okay, this is something that, no, it's good. So let's use with this one. You see? Okay, great. How to say? Okay, let me see. Okay, does it help? Okay, thank you, Carlos. In the previous chunk, I just left this code that is from the Agricola package that it will serve you if you don't have an idea how to create a randomized design for a split plot. Here you can use one of the functions that is creating designs, and you just need to say which is the main plot, which is the subplot, which type of design you have, like RCVD or you have many different options. So let's say that we have, in this case, main plot and subplot, okay? And then I'm saying I'm creating a vector here with the C, right? C is a way to create a vector. And let's say that I have 5 different nitrogen rates, the same that we have in our data set, okay? So let's see, we have our main plot object. I'm creating this way, I'm running this line. We control and enter. We can also run the subplot treatments, which is a variety, let's say width, for example. We have 1, 2, 3 varieties. So we have the main plot with 5 levels. And then within each of the levels of the main plot, we have these 3 levels of the subplot, right? There's a variety. And then to create a design, we call this function which is called design.split, okay? And then we just say, this is the treatment 1 that it corresponds to the main plot, and the treatment 2 is the subplot, you see? And then which design you want. Let's say that we want RCVD, which is randomized complete plot design, with R, which means for replications, with 3 replications. We want to randomize, right, that, and then we set a seed to reproducible. So if you are coming back later and you want to generate exactly the same design, you can come back with the same seed, and then you will get exactly the same. So let's view that. View SP design. So this way we're going to open a list that is not very handy, and that's the thing that the guys from Tidyverse changed it, right? So we had these 2 parameters and book. What is that, right? I mean, it's kind of, now I had to go and I directly want the data frame. Why I having this? So there is a way to do that. Or if you open this and go to this bottom here, you may be able to open. You see here, you have the code to open that, open in my console. So I can come here, copy and paste, right? Or another option, it could be, I put SP design, and then if I press the $sign, you have the 2 elements inside this object. So we have book. So either the first or the second, they will work both. So let's see. Okay, here we are opening. And you see you have the plots which corresponds to the main plot. That's a column, the first column. The second column corresponds to the subplot, right? The third column corresponds to the block. So let's say let's see the first 10. We have all correspond to block number 1, okay? And then we have the plot 101. But the plot 101 always contain the same treatment for the main factor. You see the main plot here is 110, for example. And then we have inside this combination of block and the level, and one specific level of the main factor, right? We will have the randomization of the subplot factor happening. So that's why the split plot, they have a special treatment of the error, because the randomization, right, is constrained. So, okay, it's the same that what happening in blocks. We are not allowing complete freedom to the randomization to happen, right? So we are putting boundaries to the randomization. And that's why we need to analyze split plots in a specific way. Okay, as you may see here, you have, for example, let's do another plot, 103, right? And then we have another rate of nitrogen, 140, and then we have the 3 rates within that. But always the 3 rates, we have a complete design, but within each level of the main plot. So that's why it's not a complete factorial happening. And what happened with this, as I put here as a warning with a split plot, is that for the inference power, it happens that the factor that we have on the main plot, right, it has less degrees of freedom than the factor that is on the subplot level and also at the interaction level, okay? So whenever we are running analysis later on to make inference, we are going to have much more power to detect differences on at the interaction level or at the factor that is at the subplot level. But the main factor, it has less degrees of freedom, okay? Okay, as I mentioned here you have the option to create a randomized design for any ideas that you may have for next year. And then for analyzing that, let me go back to the code. So again, it was this was a design with nitrogen rate as a main plot and variety as a subplot. Here we open the data, and then I call that 0 because I want to create, I want to select, and I want to make some arrangements to the data. And as you may see here, I'm creating an object that is called SplitPlot data, right? That is equal to the SplitPlot data _0, which is kind of the base version. And here I'm transforming N rate, right? This is what you will hear as a feature engineering, right? So now, instead of using N rate as a continuous variable, right? Now I want to use this as a factor. So each level of nitrogen for me, now and after, is going to be a categorical, right? A categorical variable. Is for this specific purpose, right? But you can also analyze a continuous variable. It's just to simplify the thing. But I wanted to show you that with a simple change here, we are transforming this variable as a factor with a function that is called factor. So we are saying, okay, now N rate is equal to factorize the N rate. And there you go. And now we are selecting the columns that we want. With this function select from the player, we are basically selecting a specific columns and in a specific order. So now I want my data set with block as a first column and rate, variety, and yield in that order. So let's run this. And then if we view, you see I have block and rate, variety, and yield. And if you step on the variable, right, you see that block now is a character that the software will read it as a factor. Is equivalent, not for all the models, but for this is the same. And they will have a rate that you see that now is a factor. You see the column 2, it says that is a factor with 5 levels. So that's what we wanted. And then we have variety that is a character. And then we have yield that is of numeric nature, okay? And now let's say that in this case, we don't have missing values or anything, but it's always a good idea to take a look to the data. And now we are going to explore 2 or 3 functions. The first function is what is called glimpse from the dplayer package. That is basically an alternative version of printing, but it will transpose and it will show you the data table, right? In a transpose way. So every time we have a column, it will show here as a row. Yeah, and it say, okay, it say block is a character, and here you have all the values. You say N rate is a factor, and then you have all the values. Variety is a character, and yield is an integer or numeric. Here is saying integer because we don't have any decimals, right? If you have decimals, it will interpret as numeric. So it says, you see that we have 45 rows, 4 columns, and the 4 columns are this one. It sounds silly, but having this display many times, it helps us to have a better look to the data, right? Without the need to go in and use the view function that we ran before. Then we have this another interesting function that is called scheme, right? That is what we can do when we are reading, right? The scheming technique that we are taking a quick look to all the data. So if we run this, you will see that it's producing many different outcomes. So the first one is saying the same. We have 45 rows, 4 columns, right? We have 2 of the variables that are characters. One is a factor, another one is numeric, right? Then if we explore the next one, is say, okay, we have, you see, you have no missing values for this column block and variety that they are characters. And then we have another one that is the factor, right? That we don't have missing values for that column either. And finally, we have the variable that is numeric, that is also providing a summary for that. That you say, okay, we don't have any missing values here. And then this is the mean, the standard deviation, and you have many different stuff here. If we go to the output, let me show in the web. When we have here, you see that we have all this format of a table. And if we plot here, it's producing, that is interesting, it's funny, but it's producing a histogram, right, of the variable that is numeric, trying to show you a quick look of how is the distribution of your variable. This, here you have the percent, the 0%, the median, right, the 20, the 75, 25. So there you have an idea of how that variable is distributed. So that's very useful and handy, because many times we may have extreme values. Let's say that we have our variable expressed in tons per hectare, right? So it makes sense to have all the variables. I don't know if we have width between 0 and 9 or something, right? If we have a value of 800, it doesn't make any sense. So that is very useful to those cases. And later we can produce a quick ggplot. That is basically the way that we used to plot the stuff in R, at least the way I use now. So basically we take the data set, the SplitPlot data, we create a ggplot, right? And then with this, we are adding plus after each line. So, and then we adding what in this package they call geometries, okay? So the first one is creating kind of the canvas, right? And with the second, we are adding here, we are going to add box plot, for example. So let's say what happens if we run this line. You see, we are producing a box plot. We have here, I'm saying the aesthetics, we say that the X variable is going to be an array. That is a factor, right? If it's numeric, it will fail. It won't, because it's a continuous, we need to be a character of factor. Then we say that in the y-axis, we're going to put the yield values, right? We can define that the field of each of the box plots, it will correspond to one color for each different variety you have, okay? So that's what we are doing there. If we want to add the points, we may add that with this function that is jitter, right? So there we are adding the 3 different replications for each. So each box plot is basically a summary of 3 replications. And then you have all the values. And then we may be interested on separating the plots by variety. So basically we use this function facet that is useful for creating this separation in different subplots, right? So now we see that we have a much more neat look of how the different varieties behave in terms of the response to nitrogen. And then we can adjust the scale as well. And also the theme. You see, here we adjust the scale, displaying the scale every 1000. So basically what we do here, we set the limit. So let's say I want to put, I don't know, 10, we can do that. But you see that we didn't affected the breaks that we have. So we are going only until 8,000. So now we can fix this and then we can put 10. And let's say that instead of 1,000, we want 2,000. So there you go, right? So it's very handy and it's very intuitive how to change this type of plot. It's mainly to take a quick look to see, okay, the error across the different varieties, they look homogeneous, right? We don't have any outliers, or or we may have already an idea how is the behavior of the different varieties, in this case, to the response to nitrogen. Okay, now let's go with the models. With a split plot, what we have is that, as I told you before, we had a randomization, right? That is restricted, right? So, but the model doesn't know that. So we need to tell the model we have an error at the main plot level, right? That the model is not going to read if we don't tell, okay? So what we need to specify is what is the main plot. That in this case, remember, we are telling that the main plot is basically a constraint for the randomization of the subplot, okay? So somehow the main plot is acting as a block for the subplot, okay? So that's how it's happening. We have a block already, right? Where we have located our 5 different rates within each block because they are complete in this case. But then within each of the levels of nitrogen, we have the randomization of the subplot. So that's why it's constrained. So we need to tell that. How do we do that? Let's use the NLME function, the LME function from the LME package. So to specify the model, first we need to say which is the response variable. In our case, we are going to produce a model without a split to show you the difference in the degrees of freedom, how we may get confused. So we have yield. We have then, yield is a function with the same sign, right? It's a function of, here I put 0 because I'm removing the intercept. I don't want the intercept, I just want to express the means of the different treatments as yield. I don't want a reference factor. Keep that in mind, because if here you don't put anything, or if you put a 1, it will take the first level of here it will be of the interaction. In alphanumeric order, it will take the first as the reference, and then the effect of all the rest of the treatments over the mean of the reference factor, okay? So and sometimes that could be confusing. So in my case, when I'm talking about yield, I always like to put a 0 in the front. So we'll remove that, and then you have purely yield, okay? Okay, these are the fixed components. And here we have the interaction. We have 2 factors. We have n rate and we have variety, okay? But until here, it seems that it's just a factorial, right? That the randomization happened. And then let's say that we have a random component, right? That it could be the block. Later we'll discuss if block could be fixed or random. But let's say that it's random here. So here we have our mixed model. We have fixed and we have random, right? And then we have the data. But if you notice this, we are not telling the model anytime that we have this main plot structure, main plot or subplot. So that may produce an error. So we have no split. And then we have a model, right? Where we are telling, yeah.
Yeah, so in the
This?
yeah. No, not here. That's random, right?
Yeah.
In the just before nitrate. Yeah.
Uh-huh.
Yeah. So yes.
Mm-hmm.
Explaining something. 0 versus 1. So what is the difference?
Yeah, it's what I was telling. If I put 1 or if I don't put anything, right? It will take the first level of the interaction that it will be enriched by variety. It will take one of the treatments, okay? It will take that as a reference. And then when you have the estimation of the effects of the different factors, right? It will take the effect of the levels with respect to that first. That's why I'm telling that it will be confusing later to analyze. If you have a control that in this case it will be 0, right? So in this case it will take the variety 1, 0 nitrogen as the reference, and then it will estimate the effect of all the different combinations or different treatments with respect to the variety 1, 0 nitrogen. Okay, if I put the 0, it will estimate the yield for all with respect the difference with respect to 0. So we don't have any intercept on our model. Okay, so we have all the effect of each of the, let's say that here we have 5 rates and 3 varieties, we have 15 treatments. Okay, so it will estimate the yield of the 15, right? But pure as yield. So they are all with respect to 0. So that's the difference when we put the 0 in the front. If we don't put the 0, instead of having the 15 treatments, you will get the first treatment, right? As a reference, that will be your intercept. And then you will estimate the effect of the 14 remaining with respect to the first. If you are pretty sure that the first treatment is the control that you want, keep the intercept. But otherwise, I would try to remove that, okay? Yeah.
So in terms of the value outcome, how much differences you would expect when you do one?
It depends on the variable. It depends on the variable. Yeah, exactly. Because let's say that you have nitrogen in corn, right? So if you have the no nitrogen variety 1 that is yielding 10 tons, and then the rest of the rates that they are yielding 15, right? So you will have the intercept at 10, and then all the rest, they will be, I don't know, 2, 3, 4, 5, right? So because it's the effect with respect to 10, which is the average, you know, of that treatment, of the reference treatment, which is the intercept. If you don't specify that 10, it won't exist anymore, and then it will estimate the effect of all treatments with respect to 0. So that 10, it will be 10, and the other treatments that it could be 2 because it was 12, now it will be 12. You follow? So that's why I'm telling, for me, when we are analyzing yield data, I think personally that is a good practice to remove the intercept. Unless you are pretty sure that the first is the control that you want, and then you are making inference on that. But for now, for simplicity, we're going to remove that, and that's why I'm putting the 0 on the front. Okay.
Thank you.
Yeah.
So how is the
Yeah, but it doesn't matter because it's always taking the first in alphanumeric order as a reference if you don't specify. If not, it doesn't matter the order, because if you remove the intercept, they are all with respect to 0. So it's, yeah, it won't change much. The thing is that what you have as a reference, right? You need to be pretty sure what is the intercept. If you don't know, if you're not sure, remove it, okay? Because it may complicate your inference later. So that's why I'm saying, for me, for simplicity, remove the intercept. Then if you have clear what you want as a reference treatment, that let's say you have a control, right? Then you can use the intercept. But for this purpose, I would say remove it. I mean, for the effects, the model won't change. The model won't change much. It's just the way you express, because then you will need to transform all the things. Okay. And then here you see that now in the model that we are specifying the split structure, okay? We have almost the same, but on the random component, we are saying that we have block, but also after block, we have this end rate factor, okay? So with this slash here, what we are saying is that the end rate is nested within each block, okay? And that's the main plot. So we are saying we have the main plot happening at this level. So, and this is a random component that we should account for, okay? So it's basically adding an extra random component to the model. So let's run the second. And here we have, in fact, I will run this first. I will show you the thing of the difference is in the denominator of degrees of freedom. Let's check with no split. If you say no split, you see here you have degrees of freedom. Do you see here? This column that is DF, okay? You see that N rate 0, it has 28, the same as the interaction. N rate, variety, is 28, all right, the denominator. But let's say what happened with another one where we specify the NLME. You see that the N rate has 8. So that was I'm telling, if you are not specifying this random component or the structure, right, of the error, that it was the constraint into the randomization process, you are very likely to overestimate the effect of the N rate because you will assume that you have more degrees of freedom than you actually have. So that's why it's important to specify if you are having this type of design, you need to say, where is the main plot? And then if you have a split plot, basically let's say that you have another one that is, I don't know, not a sulfur rate, right? So you need to specify the same way you specify this, right? Okay. Yeah. Mm-hmm. No, because it's just displaying the first 10. In the table, you have everything. It's just displaying the first 10 elements. Yeah, that's why when we're working in this type of files, for simplicity, is only displaying the first 10 unless you specify that. But you can explore here. You see that you have this next. If you go, you may have different things. Yeah.
So in your model specification in that fixed term, when you are using that means you are considering.
Yeah, it's considering the main and also both. When you specify with the star, with the asterisk, with the star, is the same as writing N rate plus plus variety. Yes, that's a good catch. Plus, and then the way that you specify all the interaction, it will be this way. Okay, so if you write the star, it's a shortcut to write the whole thing. Yeah. So let me show in a here. So let me show in ANOVA. Something that I like. This is ANOVA from the car package that you will find there. And what it allows us is to specify this thing of type 3. I'm not going in detail now because it's probably this is a 2-hour discussion, right? But we had 3 different types of sum of squares, as far as I know. The first one is sequential, that if you really know the order of the inference you want to make, let's say that you have nitrogen rate and then you have nitrogen source, right? Let's say that you are going to test the effect of source of nitrogen only if you know that you have effect of rate, right? If you don't have any effect of nitrogen, what's the purpose of estimating the source effect? So in that case, it makes sense to have a sequential thing, right? But the problem with that type is that it doesn't allow you to play much with the interactions, the same as type 2 error, right? Yeah, so they are mainly for the marginal effects. And then you have this type 3 that is much more flexible when you have interactions. Basically, we'll estimate the effect of the different factors, in this case, the main and the interaction once all the rest were already in the model. So in this case, the order where you write the model, it doesn't matter. If you write, let's say that you put, this is mainly when you have, in the next example, we have 3 factors instead of 2. So you have double interactions and then the triple interaction. But in the double interaction, many times you don't know what comes first, right? Let's say that you have A, B, and C, and then you have the interaction AB and BC and AC, but you don't know which one goes first. So it could be confusing. So the type 3 is flexible in that case, because it will estimate the effect of all the double interactions when all the others are already in the model. So the order you specify doesn't matter. So just keep that in mind, okay? When you have interaction, it's a good practice to use type 3. So then you have the
Say in the second model specification, so nitrogen rate is both down and in the ramp?
No, it's the end rate is not in a random. What is in the random is a block end rate. It's another. You're just identifying the subject. It's not the factor. The factor itself is not in a random component. You are saying there is a structure in our data, right? The organization, the hierarchy. We have this level, which is a combination of end rate and block, where you have something in common, right? That is the error or the randomization, right? But it's not that end rate is part of the random component. It's not that straight. Yeah, no. The end rate is fixed. It's a fixed effect. You are just with the block end rate is kind of itself of another factor that is block end rate, right? Or end rate nested in block. But it's a kind of a new variable, okay, itself. It's just to say the error is happening in this organization, right? So that's in this structure. And now we have the same, we can run exactly the same with LME4. I will leave you there the two options, right? And show you that the results are the same. See, you have here, let's check, 0, 20, 36. And here with LME4, we have exactly the same, okay? Okay, and now we may also check the different assumptions, normality, homogeneity of variance, autocorrelation, outliers, etc. Okay, so for that we have this performance package that is in the front that is producing very neat plots. We may go and test one by one, which is what I was doing here. I'll say, okay, the first check normality. Let's run. It say, okay, residuals appear to be normally distributed. So it's already running the Shapiro-Weeks test for you. And then the homogeneity of variance, it says again, okay, it's not clear evidence for this. So it's already speeding out the process. So I really like this. And then when you are producing the plot, let's see what happens. Here you have a very neat output. Here you have how your model is predicting the posterior. This is this package is making a kind of bootstrapping, a resampling of the data and generating all this. You don't need to know what is this. Mainly, we will check on this thing of linearity, homogeneity of variance, right? Every time we have green signs, right, or blue, it says that we are doing okay. But when we have red, it may be a signal of issues, right? And we have this one with the variance inflection factor that is basically telling us about collinearity, but it could be that the different factors are sharing the same information, right? Or explaining the same part of the information of the variability of the model. So we will have that in red. It's a warning. We may see this very often. But it's something that is very difficult to handle. We need to get other type of models like Lasso, and there are others that are penalizing. It's not worth it to work on this today. Just keep in mind that this is a very good way and simple, fast to get the assumption of your model checks of check. You have the same in base R. You put plot and the model, but the plots are boring. So this one, they have colors, right? And they have all this. Here we have the QQ plot for normality. You see, this is for the fixed effects, and then we have the same for the random effects. Look at this. What I was saying. You remember the assumption that we have is that the random effects, they have an effect of 0. Okay. If you see here, you have all the different combinations of, you see here end rate block, and you see that the random effect is 0. So they are not affecting the expected value. They are affecting the variance, right? Here is the same. The block is a random effect, so the effect, it will be 0. So that's the expectation. Okay, so far we are doing good, and now we have the comparisons. For this, we have this package that is a EM means. Okay, and here we are getting, we are creating an object that is a split LME4 comparisons equal to, and then I'm getting the model split LME4, right? I'm using this function that is a pipe. So basically I didn't explain that before, but it's basically creating a chain of actions of for a object, right? So here we're taking the model, and then to the model we are running the comparison. Okay. Here we put the dot sign to say that there is a mic open there. Okay. Okay. Thank you. So, so very important here. You see that here I'm specifying end rate variety. You see, and that is something that you need to tell the means, because when it's going to estimate the different means to create the comparisons, okay, you need to tell which is the most important significant effect, right? And in our case, if we go to the table before, you see that the interaction was significant. So you need to go to that level and specify that the comparisons, they should happen at this level, at the level of interactions. So we shouldn't produce comparison of marginal means within the levels of the main factors, because that is basically lying ourselves, okay?
So like this comparison will give you the comparison among the 15.
No, but you can arrange that later. I will show you. I will show you. So here we are getting this. Let me show in a second. If I'm getting this. This is only create the comparisons. Then we can make the letters and we can compare at different levels. I show you. So here you see that we have all in this table. So that is not very handy. So we need to go one step further and then use this CLD, right? That is the compact letters. Let me show. This is this is what we have as a result. Yeah, you have the EM mean, that is the mean of each of the values. You see, they are all with respect to 0. So you have 0, zero nitrogen variety 1. This is the mean, right? This is the lower bound, this is the upper bound, and then they will make all the comparisons based on these boundaries. But we need to assign letters to this. For that, we have this function that is a CLD, that is from the MultComp package. That is, it stands for compact letters display. Okay, so basically here, in my case, where I'm saying by variety, because let's say that I want to know the effect of the nitrogen, right? It's just the way we are going to arrange the letters. It's not the ways that we made the comparison. For the comparison, we made the comparison of the 15, right? But when we are showing the letters, now you see I'm arranging the thing by variety. You see? So within each variety, I am assigning letters to the 5 different rates, okay? And then we can do the same by the opposite, and rate. So you see, it will show the same. For each n rate, it will assign letters for each of the 3 different varieties, right? But the means, they won't change. What is changing is the way that we made the comparison, okay? Is that the way we assign the letters. So if I omit this component of by, we will get the letters of the 15 altogether. It's just the way that you want to make the inference, because let's say that you want to show that in a presentation, right? So it's impossible to show letters until the G, okay? So, but maybe if you accommodate, right, the plot by variety, and within each variety you put the different letters, you will be more neat. But it's not changing the result. It's not changing the comparisons. It's just changing the assignment of the letters. Okay. Okay.
In the function of the means, is it the same if I write the 2 points instead of the asterisk?
Let's see. Okay. It's the same. One change. The thing is that there you are specifying which is the highest level of interaction that was significant, because the comparison won't know that. That is something that you need to tell, okay? Or maybe let's say that you have one of the double interactions that is significant and others not. So you say, okay, make the comparisons based on this, okay? So that's the way to go.
So like asterisk and the column are the synonym.
Sorry?
So asterisk and that column is kind of same function.
Ah, here, yeah. Yeah. It's just going to take the interaction, yeah. But we can do the same. Let's say that only rate was significant, right? And then let's run it. You see? And then I'm making inference, right? But I'm having all the varieties within the estimation of the mean of the end rates, okay? But if there was interaction, this is not correct, okay? Just to keep that in mind. Okay, now let's go to a more complex stuff, which is the repeating measurements. This is very common, right? Many times we have repeating measures or measurements over time. But many times we may have other similar stuff in another dimension. In my case, you will find here in the article the paper that it was basically analyzing potassium, right, in the soil profile at 5 different depths, right, from 0, 20, 20, 40, 40, 60, 60, 80, and 80, 100 centimeters, right? So we have 5 different depths. We have different treatments that we were interested to compare 4 locations, right? But then, if you think about it, if we have a soil profile and then we are taking soil samples at 0, 20, that's the first one we take, and then we take the 2040 after we took the 0, 20, right? So we say that they are correlated, or we have repeating measures on the same subject. So we are going to the same plot in this case, and within the same plot, I'm sampling at different depths, but the subject or the experimental unit is the same, okay? So then when we analyze the effect of the depth factor, right? So we need to be aware that again, we didn't have a randomization of the depth because it was happening in the same subject. That is similar to having blocks or having this split plot. The randomization is restricted, right? So we may consider models, right, that they give a structure to this, right? And then we may have many different options, and that's the thing that I've been exploring for this paper. We are going to exactly reproduce, as I put there, figure 2. That is this figure of the paper, right? We have 4 locations. We have 3 different treatments, a pristine condition, no agricultural history. Then we have a control and a full fertilizer one. And then we are testing the potassium depletion on the soil profile for these 3 different conditions, right? So we have many different things here. Let's see that we, now because this is a spoiler, but let's see that we only have the data, right? But we didn't see that yet. So here you have the code. Let's go to R. Again, as I mentioned before, in this case, we are not interested on comparing locations as a factor, right? Here, site or location is not a factor. So we are feeding the model independently for each of the locations. The reason behind this is that all the different locations, they have very different past history, right? In between in terms of crop rotation, fertilization, many different stuff happening that may obscure the inference, right? So that way we try to isolate from that effect, and then all the inference that we did, it was within each location, okay? But we are running the same model for the 4 locations at the same time. And that's why this tidy format is, you will see how helpful it is. Okay, to read the data, I put there is an Excel file. You have here we are accessing the data folder. that is a folder that is here, okay? So to access that, since we are working here at this location within the code folder, we need to get out from that folder, and the way to say that is with the 2 dots. So with the 2 dots and a bar, we are going to the previous folder, then we open the data. So let me show you how it goes. So let's say I don't have anything, so I put this, and then I press tab, and then you see I can explore the different folders I have, okay? So there I have data, and within that I press tab again, and which file I want to open. Since the function is to read Excel files, I'm going to open the XLX, sorry. So we are open that, okay? And then something that let me show what we have until there. So we read the data, and then we will say, okay, we want to view the RM data, right, that we just created. So you say you have site as one of the columns, then we have treatment, then we have block, depth, and the variable of interest. The variable of interest is numeric, then the rest, this depth is numeric. Be aware of this, because later we need to transform that as a factor. We need to play with this. The block here is a character. That sounds okay. Treatment is a character also, right? And site is a character as well. Yeah.
So for block and depth, you need to refactor that.
Yes, yeah, exactly. So that's why we are going to transform the things you see here. And also we need to create one new variable that is a plot level. Remember that I was telling that the repeating measurements they are happening within each experimental unit, but we don't have a column here specifying that, okay? So we need to specify that. So there is a function from the player also that is unite. So here we are creating a new column that is plot, which is basically the combination of block and treatment within each of the locations, okay? And then we are going to separate that with an underscore. So I'll show you what it does. You see here that we are having the plot, and the plot is identifying, you know, that is going one level, one extra level after treat. We had a combination, but we didn't have any column specifying that. But we need that to specify the error structure later. That's what we did there. And then what we can do is to assign an ID for that. I'm not going to too many details with this. You will see how useful it is. You see that now I'm assigning I could assign a number. So I have plot 1, 4, 7. You have different numbers here. Now that they are the combinations of the 3 blocks and the 3 situations, okay? So that's that we have 9, and within each location we have a plot from 1 to 9, okay? So that those are different ways to assign this plot ID, right? Okay, and now we need to, you remember, we need depth as a factor, okay? I'm putting another function that is, instead of factor, it could be as factor, that is from base R. So it's the same. With mutate, we are creating a new column, okay? And here we are creating a new column that is depth, that is equal to depth, but expressed as a factor, okay? And then the trick here is that from one of the correlation structures, we need depth, but as an integer. That is basically because we need an order, okay? Because depth is a factor, but it's happening in a certain order, okay? So we need that for one of the correlation structures. So I'm leaving the comment there needed for core R1. We see what is later. And then we're doing the same for block, site, and treat. They are all factors now, okay? And then we may have another thing that I will explain later, that we are creating a group there. Okay, we're going to come back to this later, okay? But you will see now, if we go to the data frame, that we have changed the difference. So you see that now depth is numeric, that's okay, that we wanted, but now depth in uppercase, now it's a factor. You see, with 5 different levels. That's what we wanted. Block, we want a block as a factor as well. Treatment as a factor, okay? And side also as a factor. We are not using side because then we are going to divide, but that's the way we transform all the variables, okay, with these lines of code. Okay, and there you have the code. If you want to open directly from the internet, you can do that, but it's just for the record. Okay, now we can pass exactly the same functions before. Remember to take a quick look to the data. And here you have, okay, now we have 1 column, 180 rows, and then we have all these columns. Factor, character, integer, factor, you see, all this stuff. Yes, exactly. That's the case of them. Because, yeah, we're using the same information in different ways. Yeah. And then we can pass, again, this thing of a scheme to see if we have missing data. We see we have a missing 0. But it's, I mean, for me, it's very good because now this data set is simple. But many times you are working with bigger tables and many times you have one cell that is empty and then it's creating a complete mess. But with this, you can take a look very quick, which is the column that it has or not an empty value, okay? And then you can explore that for, here is arranging the results depending on the nature of the value. Here we have the ones that they are in characters, this one they are factors, and this one they were numerics. Okay. Now let's explore the data, the same that we did before, but with a different ggplot, okay? So we are using the box plot also. So I personally think that box plots with these jitters, right? They are a very good way to explore the data, to have a quick view. So let's say that we are going to create box plots. But you see here, we are reordering depth in a descender order because I want to express that. I show you what I want to say. You see that now I have depth, but it doesn't make much. I have depth on the minimum depth that is 10 centimeters. I have it on the right side. And then we have 90 on the left side. So it doesn't make any sense, right? So what we can do, we have this function that is called flip, okay? And here we have all sides at once. But let's say that we're going to, oh, sorry. Yeah, sorry. So now with this core flip, what I did is I changed the X for the Y and the Y for the X, okay? So now it makes sense, right? So I have here I have the topsoil, right? And then we're going down, right? And then we have this 10 centimeters, 30, 50, 70, 90, okay? So for this place, this is the way that it's on the field, right? So I have soil depth on the Y axis now, and the soil test scale level on the X axis. But now what you can see here, for example, you have 4 different locations, and you have 3 different colors, which are the different agricultural situation. What calls your attention here? Is there any color that it seems to behave different than the others? Exactly. So if you see here the box plot with blue, the pristine, what happened with that? It has a higher value, but what it has also? What does it have? Yeah, exactly. The variability is different. So that it may tell us, okay, pay attention because it's very likely that you don't have homogeneous variances. So if you are planning to run an ANOVA, a normal ANOVA, it won't work, or at least you are violating one of the main assumptions, right? But you can still, if you are able to model that, you can go perfectly work with that. And that's the flexibility that many of these packages can bring. So let's see how we manage that, okay? So we have many problems going on. We have the the repeating measures across the space on soil depth, we have this different variability depending on the different treatments. So let's see how we can manage that, okay? Okay, let's start with a reference model for a non-mixed model, okay? We have a block that it could be fixed or random, right? There is not a correct way. It could be whatever you want. It depends on what is the inference you want to make, okay? In my case, if you ask me, right, I'm never interested on the effect of block as a factor, right? For me, the blocks that we may have on the field, they are just simple representations to constrain the variability that we have, or to assign a value to a gradient of something that we may have, slope, fertility, whatever, right? So that's the way that we work with blocks. So if we assign them as a fixed factor, let's go to the web page now, sorry, because here it will be much easier. Okay, here we have the two models. On the top, we have the fixed model, right? You say we have the, sorry, but it's always very important to write down the model because it's the way we realize what's going on. Okay, in our model, let's say that treatment for simplicity purposes, treatment is a combination of the condition, agricultural condition and soil depth, okay? For simplicity. So here we have we have 5 different depths and 3 different conditions. So the treatment here is representing 15 different combinations, okay? We can segregate that into the factors, interactions, but for simplicity, let's keep it this way. So we have mu, that it could be if we have an intercept of the overall mean of the model, okay? So for each observation, for the treatment Y and block J, okay, we will have the overall mean plus the effect of tau I is the effect of the treatment I on mu, right, over mu. And then you have the beta here, beta J is the effect of block J, also mu, okay? And then we have the random effect, the epsilon AIJ, sorry, that is the effect of that replication, right? On the mean also, but if you see below, we're specifying that is expected to have a mean or expected value equal to 0, right? And a variance equal to sigma squared E, okay? So that way we're telling this E epsilon is a random factor because it doesn't have an effect on the mean, right? It's simply representing the noise around the estimation mu, okay? But it doesn't have an effect on the mean, on the estimation of the mean, okay? But block here it has, because we are not saying anything about block. So here block is still fixed. Okay, now let's go to a model where we have, let's keep it there. So if you see, we write down the same. You see that the expected value of the observation Ij is equal to mu plus tau I plus beta J plus epsilon Aj, okay? But here, you see, we are adding this magic thing, this equation below, that we say, okay, we have the block factor on our equation, right? But that has an expected value of 0 and a variance equals sigma squared B, right? That is the variance related to the block, okay? So that's where we are specifying the block. It doesn't have an effect on the means now, but it has an effect on the variance. So many times what we are going to have is that if you put block as a random effect, right, you have your means noisier. So your confidence interval of the means, they tend to be wider, right? Because now you're adding an extra variance component, okay? Sometimes, very often you will see that, okay? There is a lot of discussion of this because the thing is that ideally blocks are random because they are just, let's think that blocks are since we are trying to reduce the effect of a gradient that we may have, slope, fertility, whatever, right? Let's say that we put 3 blocks, but why no 10 blocks or 4 blocks or 7 blocks? That's why we say that the number that we use is just a random representation, right? Of all the potential blocks that I could add, right? The problem is that normally we put only 3 blocks or 4, in the best case 5, 6, with good luck, right? But what happens that to evaluate the random factor, it's very likely that we need more than 5, 6, okay? So if we're analyzing block as a random factor, the ideal condition if we have as many as possible, okay? But either way, block fixed or random is okay, okay? As long as you specify how you did it, it's fine, right? There is no correct or bad answer. It's your choice. And always ask for a statistician for this, okay? It's always a good advice. Ask, how should I treat my blocks, okay? Okay, that's the main difference. And then to specify that, let's say in the first, model, right? The simplest model, what we call here M0, with block fixed, we just say, okay, we have treatment, we have depth, we have the interaction, right? And then we have block as 6, okay? And then we have any specification from the random component, because the random component it will come later, and it's just a random error, right? Is that you have 3 different levels of blocks, right? So the computer will automatically read that. And then let's say when we write the effect of block as random, is simply saying, okay, random is equal, right? And here we say 1, with 1, we're saying that the intercept is different for each block, okay? So here you see that I didn't remove the intercept, I just put 1. So it's taking one of the values as a reference. And then we have the block. So we had intercept, we should put the 1 there, right? If we don't have intercept, we don't need that one, okay? Anyway, so that's, yeah.
So in the first case,
The first.
model, that one is the fixed model.
Yeah. Yeah, we are just specifying the fixed part of the model. We don't say anything to the random. So the only random component is the error, right? Is the leftover, I would say. But here we say, okay, pay attention, because what we are saying with the block as random, we are saying that all the treatments that are within the same block, they are sharing something, right? They are sharing the same level of a gradient of a slope, or that's sharing the same level of fertility, right? Or something like that. We are just saying, pay attention, because within each block, there is something going on that I'm not interested in making inference, but it's playing a role there, okay? So that's the thing that we are doing. Now I put 1 because here I didn't remove that. So we are saying that we have 1 different intercept for each block. Yeah, that's, I mean, yeah, if you run this, you're going to be fine. Yeah, no? We don't want to complicate the stuff. We have time to complicate. Yeah, but yeah, no. Okay, but until now, we have these 2 models, and I would say M1 is better for me, right? But still, we have unsolved this problem of the correlated, the repeated measures, right? And the different variances that we have. So we need to somehow address this, at least to test different candidate models to see which one is doing the best, okay? So now let's say that we have M1, right? That is having blocks as random, right? I'm sorry, I didn't go in detail, but for me, I find this much more straightforward later, because here we are defining a function. So I'm leaving you the code there. So you can define the model as a function, and then you can pass the function in a pipeline. It's much straightforward to do that. So we see that in a second. So here you see what we can separate the different functions for the different models, and then we run the same function for all the locations at once later, okay? Many of you already know this, but it may be helpful if you know. Okay, now let's say that we have block as random, but we are interested in adding another structure that is a compound symmetry. That is basically adding another level of block. That's the same. So when we are saying that we have blocks, we are saying that our model has a compound symmetry within each block, because we are saying within each block, we are sharing kind of the same variance, right? So it has no effect on the mean, on the expected value, but it has effect on the noise, right? So we are telling the observations within each level of blocks are sharing something, okay? It's the same. So in this case, we need to specify that for depth, okay? Remember? So here we have the same. We have treatment depth and treatment depth interaction as a fixed component. In the random component, we have one and block, right? See? But later on, we define this, and this is something that LME has that LME4 doesn't, which is the possibility to specify correlation structures or weights to the variance. So here you see, I'm saying we have a correlation happening, right? In a core compound symmetry, that's a function, right? And the form is that the depth, right, is a factor that is playing a role there as a block. That's why I'm using the depth, which is the column that is a factor, because it doesn't matter the order, right? If it's 10 or 20 or 30 centimeters, it doesn't matter. We are just saying that each of the 5 depths, they are sharing something, but it doesn't matter how far they are from each other, okay? And then we're saying this is happening at the plot that is nested within block. Remember that we did that game before? So that's the thing. So here is a subject. Here is a subject where the repeated measurements are happening, okay? So we're saying within each of this subject, we have something going on with the depth, right? So block the depth or use depth as a block. So that's what we are saying there. And then we may have another structure that is very useful in business when they are estimating the trends on prices and that stuff. That is the autoregressive of order 1. So that's basically saying that the depth number 1 and 2 are much more likely to be similar than if we compare depth 1 and 5, okay? So the distance matter. So we have a correlation structure where we are specifying that 1 and 2, we do that with here you see I'm putting an exponential thing. You see the distance, depth 2 minus depth 1, that's the distance between the depths. And then we have, you see here I'm specifying that we have this row that is specifying the correlation between the variances. You don't need to know much, just be aware that this correlation structure is considering the distance between the depths, right?
For doing that's why you pass it as an integer.
Exactly. So now if you see now I have a correlation R1, but the factor that I'm passing here is the thing that is a number, right? As an integer, because here the distance matters, okay? Matters. But again, we are saying, okay, it's happening at this experimental unit, okay? But now consider the distance between the different depths. But again, it's the same. We have LME, we have Soltes K. As of with this, we are specifying the fixed component. The random components is just block, but then we are saying, be careful because we may have this correlation of error between the different depths, that it depends on the distance. And the next model that I also tested, it was a model that is the number, sorry, here is my mistake. Or, yeah, here is not M2 plus heterogeneous variance. Because the M2, the M2 is this one with the compound symmetry. I'm not going to explain that, but I mean, we can pass together the R1 with the heterogeneous variance. So basically we need to consider that as a block. Anyway, but the thing is, if you remember, we have this different size of variability on the pristine conditions that they were not the same as compared to the control or to the MPS fertilizer treatment. So here what we are saying is we're putting a weight to the variance, okay? Many times we may have, if I use a, I think that we have a Sharpie. Here. Let me see, it will just take a second. But many times we will have something, let's say that it's not this case, but let's say that we have nitrogen rate, right? Or fertilizer rate. Use, yeah, probably you will see. And then we have yield here, right? And many times we have here the expected value. Let's say that this is the response, but then we may have a variability that it could be something like this, or it could be the opposite. Let's say that we may have something like this, right? So here, if we have the dispersion of our data points, right, like a triangle or something, we have a structure. We don't have homogeneous variance across all the levels of our factor as explanatory variable. So here we can pass away, for example, because we say we expect that as the higher the rate, the lower the variability. Okay, so we can pass away saying it could be the square root. It could be many different combinations. In this case, what we have is you see, here we created these two groups. Let's go back to the code. I'll go here. Then I go to repeated data. Here you see that we have group, and then I'm creating a group. If the treatment is pristine, it will say pristine. If not, it's agriculture. And these two groups, they are the ones that they are likely to be different in terms of variability. Remember, if we see this plot, okay, if we see this plot, we see that both control and MPS, they seem to have similar variability across the different depths, right? But the only one that is different is a pristine. So what we do here is to create two groups. One group is this one, only considering the pristine, and the other two, they are belonging to another group. So again, we are creating a block, right? So that's basically what we are saying. So how we specify that? When we go to the candidate models, and then we have, here is, sorry, M2 plus heterogeneous variance. You see that we are in a way, and we say that we have an identity of the variance. Yeah, I'm not going to detail that, but we see that the variances are different depending on the group. So that's the thing that we are specifying there. You see, this very similar to what we say with block here. You see, it's some of the same syntax. We are saying here that the form of the variance, it depends on the group that we have. Okay, there we have the 4 different candidate models. And now let's see how we run all at once with in a pipeline, okay? So we're creating an object that is a STK models, okay? And then we are taking the data, the RM data, we pass a pipe here, and then we are grouping by site because we are going to run the analysis side by side, and then we are going to nest. This is important, and for me, it's useful. There are other ways to do that, but let's see. So I will show you view. I will put STK models. You see, I have site 1, 3, 4, 2, whatever, and they have the data. So you see that inside each of the cells, we have an entire data frame. If we open the data, you see, we have all the data for that location. So now what we're going to do is we're going to pass a function that is going to run, okay, for site 1, it will take this and it will run analysis on this, okay, on each of the cells. And then here in after, we're going to add column after columns with the different objects. So I will show you that in a second. So now let's say that we are nested and then we run model 1 and model 2, okay? Let's see. Oh, What's going on? Model 1, blah, 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 blah. What's going on? I need to run over again. Ouch. Okay, I want to close. Okay, close, close. Okay. I'm running all the thing, but then now I'm going to show you what we did. So each time we are creating a mutate, okay, we are creating a new column. And that column, it will contain model 0, model 1, model 2, model 3, model 4, right? All the models that we defined before. And then after that, we're going to rearrange. Okay, let's see. Okay, now. You see that we had at the beginning, we only had these two columns, site and data, and then we added model 0, model 1, model 2, model 3, model 4, and that's it. Okay, we had the 4 models within each of the cells. We had the one model for each of the different sites. Okay, so we have model 0 for site 1, 3, 4, and 2, the same for model 1, model 2, etc. And then with this function pivot longer, what we're going to do, we're going to flip the data. I'm not going in detail. You have the code there, explore. But let's say that if we run all together, here we're passing this function augment from the Broom package. Remember that I mentioned that it was useful to arrange the models in data frames. So that's what we're going here. We're going to function augment and then the function glance. Let me show you what we did here. Okay, and then we have, you see now I rearranged everything. I put the models in a column. So we have for site 1, we have repeated this thing and we have model 0, 1, 2, 3, and 4. And then we have the model, right, for each of the cases, the results of the model, the performance of the model. So let's say, let's open this one, right? So here we have the data, but to the data, we are attaching the fitted values, the residuals, right? All things that are useful for checking the assumptions later. And then we have the performance. Let's open this one. So see, for each model, we are estimating, okay, we have 45 observations. This is the variance. This is the likelihood. This is the AIC. This is the BIC. And we are going to use this to compare the different models, okay? Okay, we reach until here. So now we are going to, with this function extract AIC, what we're going to do is we're going to take that column performance, and from that column, we're going to extract the value AIC. You see? I'm interested in only that value, AIC, because I'm going to base my comparison of the models on this, the Kaike information criteria, okay? And then here you have the value. So basically the lower, the better. And then we can also extract the coefficients, and then we can also run, I will run all now. So we are going to store all the plots for checking assumptions. We are going to store all in the same data set, in the same data frame. Here is a warning that is being produced for this performance checking, but let's see how it looks. So we have the AIC, here we have the coefficients of the model, and here we have all the checks. And each of the checks is basically a plot. So if we go here, let's say STK. You see, if I'm open that object, it's a plot. But later, this is tricky. We're going to extract them later, okay? So now let's say that we have these locations, site 1, 2, 3, and 4, but now we're going to filter and I'm going to separate that. And here I'm generating a tab, and in the, you have the code here. So let's see how I created the report. I have all this confusing stuff, but then I was able to summarize this. I have all the code here before, but let's see here. I'm showing the checks of the results of the model for the 4 different locations in tabs. You see? So I created kind of panels. So here you can check for site 1, for site 2, for site 3, for site 4, right? How the best model was. Okay. or not the best model, it's the model number 1. But we have this for all the 4 different models. We have this for the 4 different locations, but you have all at once in the same data frame. Okay.
Would you base your model selection only on AAC there, or
Mhm.
you check the plots also?
Yeah, also the plots, but yeah, I did both. Yeah, exactly.
And I have a question. Is
Mhm.
there any, like, so you're picking the model with the lowest AAC.
Mhm.
And they say you have a model there, you were having values around the 300 range.
Mhm.
The AAC. So let's say you have a model of one that says 307 and the other says 306. I mean, is there any criteria for like a marginal decrease in AAC that would tell you like where you should stop? looking
Normally,
for more?
yeah, normally they say that the AIC is already penalizing by the number of parameters. So the more complex the model is, the AIC is supposed to be already lower, higher. Sorry. So if you have more variance parameters, more fixed parameters, whatever, it's going to penalize your score. Okay. The thing with the AIC is that you can compare, you should compare models that they are only running on the same variables. If you have one model that is using transformer variables, another one that is using non-transform variable, that is not a valid comparison. You need to compare models that they are running on the same data. That's very important, okay? So if you are running transformations, AIC or VIC, they are valid if you are comparing all models running the data, the transformer data, okay? It's not that you can compare the transformer versus with AIC. With that, you will base on the assumptions because many times you transform the data to fix the normality, right? In my case, after talking with several statisticians, if you are able to figure out to model your data without making any transformation, the better. So let's say the heterogeneous variance, right? Many times we want to force our data to be homogeneous in the variance. So we may use a ranked variable or many different options. But then we are losing interpretation. So that's a problem. So, but if you have a model that is where you can relax this homogeneous variance assumption and then you can deal with different variances, better. But in that case, you can compare with the AIC because the model that it has the heterogeneous variance, it has more parameters than the other. Normally, the rule of thumb is that if you have the AIC that is 2 or ideally 5 lower than the competitor, is better. And then you have different options like the corrected AIC, or you can estimate weights that they are more complex. I didn't want to go in detail because but you may have options that you can compare kind of 4 models and then you create a ranking of the 4 models with a weight. Yeah, I mean, we can talk more in another occasion.
I have another question. So you were running a model, the model by site.
Uh-huh.
I'm assuming that you were not interested in looking on the site effect.
No.
But what would be the case that you will run the model, include site as a factor of the model?
If you are interested in comparing locations for very specific reasons, you can do that. But the problem you have, remember, is that the randomization of site is not possible. The site is there. So that's the problem. Many times it's included in our models as a factor, but the problem is that it wasn't randomized. The site is always there. You don't have replications, true replication. So it's always the case that if you have different years, they are pseudo replications of site, right? Still, you can manage with different models where you can model these components. But in my case, I want to play safe in that case because all the comparisons that I can make later, they can be obscure. In my case, I already knew that the different locations, they have very contrasting history. I mean, previous the start of the experiment. Yeah. Mm-hmm. Yeah. Uh-huh. Yeah, exactly. Sometimes you can help with a covariable. Yeah, that is helpful. Yeah, that you can add that to the model also. Instead of using site itself, you can use a level of a factor that you say, okay, site is supposed to be explained by different soil and weather factors, right? So you can add those factors but again, the randomization is not there, right? So, but you can add a weight or something to the model based on precipitation, or yeah, you can do that. Yeah, there are many different tricks. Here I'm showing the simplest ones, and in this case, I didn't want to complicate the model too much, okay? So that's why I just decided to run the models independently. And then all the inference I made, it was within each location. I'm not comparing site 1 is better than site. No, I cannot make any comparison on that.
So is that kind of adding covariates in your model?
And you're adding in the correct, when you have the variance covariance matrix, okay? You may have the ideally you have identity where the diagonal is you have a 1 in the correlation and the variance in the covariance. The variance covariance matrix you have in the diagonal, you have the variance, right? And then if you have covariances, you will have all these weights, for example. But you also have the correlation matrix, right? Basically, you are multiplying one matrix by the other. That was the models are doing in the background. In the correlation matrix, the correlation is basically values between 0 and 1, or it could be negative also, minus 1 to 1, sorry. In the diagonal, ideally you have 1 because with itself is the correlation is 1. But then if you assume independence, all the diagonals are 0, right? Or the off diagonal is 0, okay? But if you don't have zeros, you can add something with a correlation structure like the compound symmetry or the R1. We are saying, okay, on the off diagonal, there are not zeros. There are numbers there, okay? So that's what you are adding more. Yep.
Quick question, maybe you have mentioned this, so sorry if I missed.
Mm-hmm.
But just following up with the Nico's question,
Mm-hmm.
he mentioned about sites. How would you do if you had different years for same sites there?
That's a good question. Again, you may have different years may differ on precipitation levels, right? So ideally, instead of using year as it goes, as year, I would try to use a variable that explains the difference between years. So you can add that as a covariate in your model. You can add that as a factor, yeah.
So you prefer like adding like weather information?
Exactly, because you are adding information basically. Because if you are saying year is not saying anything. It's just A, B, C, or 20. Yeah, it's a. Yeah, exactly. If you have something that it may explain you may. I mean, it's better if you add it. Yeah. Yeah, and there are many different tricks. Again, probably I'm not the most expert on this, so that's always good to go to a statistician and ask how you. Yeah, don't be afraid to do that. I mean, worst case scenario, yeah, you're shaking hands, don't understand anything, go home, and but everything happy. Your advisor happy because you went to the guy or to the lady. But no, but do, because I mean, many times at least you will understand something of what he's telling, right? And yeah, yeah, don't be afraid, just go on. Yeah, maybe if you just understand a couple of words, it was just. Yeah, if I'm yeah, I'm happy to help you. Okay, so let's keep moving because we are already 2 minutes left. But anyway, I knew that maybe we have this scenario. You have all the code there. If you go to the web page, it's all there. It's not a nuclear device code. So yeah, I mean, what's the point of hiding the code? I don't know. Don't hide the code, please. Just share it. I know that I understand that you can share the data, but the code, come on. We are not making any, we are not discovering, we are not for the Nobel Prize. Yeah, so okay, and I hope that this will help you to have at least a skeleton, right? Okay, so let's see now, because now we want to identify which is the best model. Okay, So here I put a code where I'm grouping by size again. So I'm taking all the models already, the data frame with the models. And then I'm creating a mutate and I create this is a logical function, the case when, where I'm saying if the AIC is equal to the minimum, that is the same as saying, okay, this is the best model. Okay, so I'm putting a yes if it's the best, no if it's not. Okay, so that's the way we're creating this thing. So let's see how it looks. So here we are creating a very simple plot where we have all the different, the 5 different models. You see with the block as fixed, you see the AIC. So it was better with block around, right? It was better, a little better. So you see an AIC of almost 500, then we are able to improve that. And then we add more complexity, but we are also increasing the power of our model, okay? And sometimes probably with the second model, it was already fine, okay? We didn't need to add or adding this correlation or multiple errors. If you go to the plot, very quick, you see that here inside 2, it was probably the only case where this heterogeneous variance is not playing a role. So there it wasn't, I mean, it wasn't worth it to run this very complex structure, okay? So that's why we need to do model selection, because we may have a structure that is very complex, but there is no recipe that fits all, right? Okay, so let's go back to the code. Sorry, here we have the model. So basically later on, we're going to filter and going to select if the best model column say yes, right? The row, we filter and we only get that thing. So here we have the model effects. Yep.
A quick question.
Mhm.
So, for example, on site 2,
Mhm.
you choose model 1 because you already got a good fit for the.
No, I'm choosing model here. The best one is a blue one, the blue triangle.
Sorry, for site 2.
Site 2, I'm choosing model 1. Yeah.
Yeah. So, I'm assuming that you choose model 1 because it's of the simplicity of the model.
Mhm.
Yeah.
Yeah.
But then, for example, why on site 4
Mhm.
would you rather model 2 instead of 1?
I don't remember exactly the difference between these models. Let's see. So site 4, we have model 1 and 2 is 12 and 13. What? Oh, sorry. Yeah, probably remember that the rule of thumb is that you have a difference of 2 or 3. Probably in the plot is not very clear, but let me see. Can see that. AIC. Yeah, you see, I don't remember if it was exactly this 12 and 13. You see, one it was 328 and the other one was 24. So it was a difference of 4.
Gotcha.
It doesn't matter magnitude. If you have a difference of between 2 and 5, that's good enough to select the model. Yeah. Otherwise, you can if they have different AIC, you may go with the simplest. Yeah. Yeah. Yeah, but that's a good point. It's always many times you don't need to base the selection on the AIC only. You may say, okay, no, I want to make inference or with this structure of the error because it's a safeguard or something. The only thing is that the model it could be more complex unnecessarily, right? But it's a valid choice also.
Would be possible to merge
The models, I don't know. For machine learning, it's easy to do ensembles and that, but for this type of models, I don't think so, because then the inference that you are making is a mess, because you need a likelihood that is a distribution and it is different, but depending on the model. Yeah, but at a first glance, I would say no, but probably yes, but it sounds complex. Yeah, I mean, instead of doing that, I will use a simpler. Okay, you see that here I'm doing this thing of selecting models that I'm getting the best. Okay, so I'm creating that thing. Okay, and then I'm getting the selected models, and then I'm passing a mutate and then getting the ANOVA for that. Okay. Oh, sorry, I need to create that. So if we run this and later we run this, and let's say for side 1 we have this. Okay, this is for side 1, and then we may have the same for side 2 and so on. Okay. Oh, sorry. But it's the same format. The only thing is that, you see, this is for side 2. And if we open the data set, the data frame view, and then we get model effects. Sorry. We are just about to finish. You see the same. I study in data frames, and then we have all the stuff. The only thing is that I really get rid of all the other models, okay? Because we don't need them. And then here we have the results of the ANOVA for side 1, side 2, 3, or 4. Okay. So that's the thing. And then we need them comparisons, because now we knew that probably we have this double or triple interaction. It doesn't matter. What matters is which one was the most significant. Okay. I will tell you that in all cases, the interaction, it was that there by treatment, it was the main interaction. So all the comparisons that we are doing, you see again, they are based on this level, okay? Because it won't be correct to do the comparisons based only on treat or only on depth, because we have an interaction going on. So there's a confusing effect. So basically we're doing the same like in the previous data set, but here we are creating the data frame, the tidy structure, okay? And later we do the same, we pass this map function, and then we are creating the CLD to assign the compact letters, okay? And then we are comparing, in my case, I wanted to display letters within each step, because within it, I didn't want to make inference on the difference between depths, but I wanted to compare within each depth. I wanted to assign letters to the different treatments, okay? So that was much more, or you can do both. I remember that once I used, so let's see if once I use a .df, let me show. I didn't want to complicate much the plot, so you see here you have all you are producing this. I am nested all the stuff. I'm jumping several steps, sorry, but here you have all the group, but all the letters, if you see, they're only A, B, C, no more than that, because they are happening at the depth level, okay? If I'm not saying that, the comparison, it could be much more complex, okay? But now I'm constraining that, and I wanted to compare, for example, here at the depth of 10, I want to compare the 3, so the 3 were A, B, C, right? And the other one, it was A, B. But I'm not comparing, for example, and in the control, I'm not comparing the depth at 10 or versus the depth at 70. I'm not making that difference. So that's how I assign the letters. Okay. And then here, a little trick that I did, it was to assign, here we are going to produce the plot. Remember that we want to do exactly the same that I did for the paper. Here I create the colors that I'm passing later. And here we create the ggplot. We get the plot data frame that I got there, here, the ones I showed before. And here we have different tricks. You can explore them later. I'm reordering the level of the factors, right? Depending on the order I want to display in the plot, okay? So in my case, for example, for the treatment, I want the legend to say control first, then MPS, then pristine, okay? And for the facet levels, I want to say side 1 first, side 2, side 3, side 4, okay? Okay. And then here we have how you put expressions like the subscript or superscript, right? So here we have the trick how to do that with the big quote or expression. Here I'm saying that I want to display one plot per site, you see, in 2 rows. So I want a plot that is a square. So let's see if we plot that. You see that here I'm saying that, but I only had the canvas. I didn't pass any geometry like the points and the arrows. I didn't pass anything yet. You see that the jump point and the shapes and everything is after that part, okay? So that's how the ggplot works. We create a ggplot. I'm saying I want 2 plots. Here are the laps of the different axes, and now let's add the points, okay? So let's see. So here we are the points, but you see that the depth is on the X. Again, so we had to flip that, and then I don't have any error there. So what I'm doing later on, let's see, I'm adding a little more complexity. You see, I'm adding the colors now, and then I'm planning to add the error bars that they are coming from the means comparison from this means function, right? So it's all coming from the models, right? So here you see that I'm in the bars to the plot, but still I need to connect the trajectory of the depth, right? So we can do that with a jump line. So that's the way we go. And then the next step it will be to re-express the scale of I'm reversing the scale. You see, I mean, these tricks are awesome because you can do almost whatever you want. You see, I already making some transformation, and now what I like it the most, it was this flipping the coordinates. So now I have finally what I wanted, okay? But it still is not the final format. There you have all the themes where you can select different, where you want the legend, etc. So the final plot, it will be something like this, okay? And this is the thing that we have in the paper. Remember, figure 2 is exactly that one, okay? So that's the way, you see? And then what I did here is just to display that in a panel. So if we go here and then we add the plots, okay, you have the figure displaying a panel. You can adjust the size and everything. Here you have the code in each of the, remember, when you go back to this, you have all the code to generate the stuff, okay? So yeah, just play around. And after that, I wanted to add this because all this web page and everything with the table of contents and everything is all made in the same file. So I'm having the analysis, but I also created a blog. So let's say that you want to create a paper or something, a report, right? And then you want citations. And this is a very awesome trick that I added with this cuarto that it wasn't in Markdown available, but it's using the visual editor to add citations. So let's see how it works. So let's see that I'm missing a citation. I don't know, I didn't cite the tidyverse, okay? So here I will add all, or I would say tidyverse is awesome, whatever. I'm biased, you see. And then tidyverse, but I want to add a citation. So the good thing is that if you go to visual, it's kind of moving to a different, how to say, interface, okay? And here you have all you see the images, etc. So you have all the kind of a previous version of how it looks. You see all the code. And then let's go to the end where you have these adding reference citations, okay? And here saying tidyverse is awesome, but now I want to add a citation. So I want to go to insert and then go to this citation. And then let's say that I'm looking for an R package. And then I just need to type here, tidyverse. You see, tidyverse. I select that, I put insert, and it's the thing is there. It's already there. And now it will add this to the report. Let's see if I can render this to the HTML. Let's see if it goes. Oh, yeah, there is an error there on 372. Ah, sorry. Yeah, but basically what it's doing, 372, I think it's something going on there. Should run. Let me try again. Yeah.
Read that data file before running it.
Nah, probably.
From scratch, I think.
Let's see if it's giving me the same thing. How this view that they may cause some issues. Putting again 572. I think it's the view. I think it's the view stuff. Yeah, because besides that, I didn't change anything. So let me say, look at this view. So you see that you have this thing of view, okay? But let's say that I want to remove all of them. There is a trick that you can set as I did it with Control D. So I can look all the times that I have view, right? And I have that. And if I want to modify the text, I do all at once. So I can delete that or whatever. So let's say that I want view parentheses. I want to delete that. So now I'm looking all the view parentheses and I can remove them. The only thing is that what we have inside is not. Anyway, so let's see. Yes, Control D, but you need to set up in a shortcut. Yeah, I can show you another day. But you can set up in the global options. There is a way to add new shortcuts. Okay, so let me try once more if I can render this stuff. So and then with this adding citations, you can look for in the cross-reference database. 80%. Come on. Yes. Went through. Okay. Let's wait a second because it's producing all this stuff, right? So it's producing the web page that was but local. Oh, there was an error. Okay, this happens a lot. So, but basically, let's go to the web page. So every time you do there, you can look with a DOI. So if you just have the DOI, you look for there, and then you will add a citation with all the formatting, everything you want. So that's very handy, very, very handy. I mean, until now, I didn't find anything Sotero or whatever that it works fluently. And then you add that, and automatically it will add this in alphabetical order. It will add all the citation with the proper format you want. So you can specify which format, the Chicago, APA, whatever, okay? But it's automatically adding this with the format. Yeah, and then all this stuff of the colors, here you have the links, you see to my LinkedIn, here you have a search thing that I can look for whatever, I don't know, NLME, right? So it's looking all the times that I mentioned NLME, so you can look inside the code. Okay, guys, I hope that this helps. You have all the code there, download this repo, play around, use it and improve it. Okay, thank you, guys. I stop sharing.